background, and I think thank you very much for attending this. And in terms of my own background, I think if quite a few of you may know who I am, but I've been an Arctic practitioner for the last 35 years, starting my Arctic career in Yellowknife and having a residency period in Iqaluit and Whitehorse. So it was 5 winters in the north of the last 35. And that practice has been in water and sanitation. And I guess I will just get on with this presentation. So the climate change impacts on water and wastewater systems in the Canadian Arctic is actually based upon a study that I was engaged through the National Research Council of Canada to look at that. And I certainly want to give credit to Andrew Colombo with NRC and Yehuda Clymer with NRC, that they were the ones who engaged me now a few years ago and allowed me to do the research that sort of brought into this presentation, which I've added to. I also have a special thanks to Rick Campbell, who's the infrastructure director up in Inuvik, who's provided some photos for this. The presentation is going to be from coast to coast to coast and a little bit off the coast. So I want to get into some of the background of the study, the information I prepared for the NRC project, but as well, I think it's really, really important to delve into some actually specific locations that there may be climate change impacts on infrastructure. And I say may because I think most of us know in terms of climate change, definitive evidence is really hard to say, but there is something happening in terms of a dynamic. But, so I want to present sort of examples, going across Canada, Dawson, Inuvik, Yellowknife, up to Greece, and then going a ways off the coast up to Svalbard, which is the island north of Norway. What happens when the Arctic thaws? So these are some pretty dynamic and very visual photos on what is happening in terms of thawing or warming of the Arctic. And for lack of a better phrase, I would say the Arctic is falling apart. And on the scale of these photos, you could say, yep, that's pretty much what's happening. And, the text that I've got here is that on October 30th, 2019, researchers from McGill stated as the permafrost continues to degrade, climate in various regions of the Arctic could potentially change abruptly and in the relatively near future. With the work I did for NRC, the original compilation was to try and find, I guess, specific occurrences which could be construed in terms of climate change in the Arctic. So that compilation was characterized in water supply and treatment, sewage treatment, and water and sewage conveyance. So in the water supply treatment, I went through and just looked at various communities in the Arctic: Cambridge Bay, Sanikiluaq, Kugluktuk, Grise Fiord, Yellowknife, and the list goes on. And certainly this list will be available with the presentation for anybody who wants it. And I think another aspect is the actual report I prepared for NRC is available. So this information is in that report. But as part of that, if you look at the Cambridge Bay water supply, there's apparent change in the raw water quality from the original design criteria. So the response to this is process changes may be needed due to the change in the going down to Kugaruk, the change in the water quality. Kugaruk is suffering from a saltwater intrusion up the water supply river. So this is, in terms of response, is manifesting itself as the potential water supply identification and utilization as required. If we go down to Yellowknife, there has been probably over the last 15 years a change in the water quality with the Yellowknife River, with increasing turbidity and low water. So they do have a new water treatment facility that was, I think, commissioned now. That's probably getting upward 6, 7, 8 years ago. But in having the having the facility and intake completed or revised or adjusted in terms of those water quality issues. Tuktoyaktuk is another one, is that they have a change in water quality, a water level reduction in the intake water supply lake, and they are having observations. I mean, Tuktoyaktuk is unique that they have an earth water reservoir that they fill once a year from a tundra lake, And what I think one of the issues there as well is this tundra lake is actually, the water level in that lake is actually decreasing because, of course, if you're up in the Arctic with permafrost, is the retention, what is holding these tundra lakes in place, or retaining the water is in fact sometimes, quite often permafrost and frozen soils. So if we go down to sewage treatment, Cougaruck Sewage Lagoon, their lagoon is leaking. And I've been part of a site investigation and part of input in terms of remedial action developed, and it has been executed. I think ultimately what they did there was they put in a liner. So it was an earth lagoon originally with a partial liner keyed into the base of the lagoon and into either rock or permafrost. And they've had to completely reline that lagoon, which is of course an extraordinary expense. It's a multi-million-dollar expense. In Kugluktuk as well, and I'll provide some more detail on that, their lagoon is leaking as well, so that a remedial plan is being developed and will ultimately have to be executed. But again, we're talking about, in terms of the remedial action, these are multi-million-dollar exercises to be undertaken on these sites. And in combination with that, all of a sudden the wastewater treatment process that's in play, it now has to be taken out of service. And from the regulatory perspective, they look at that and saying, okay, you're going to be interrupting the sewage treatment. What are you doing in the meantime? What contingency plan are you have in play that is treating the sewage during this remedial work? And the regulators, and they're just doing their job, they're stating, that, well, you can't just discharge raw sewage. You have to provide at least an equal or not better treatment system. In terms of water and sewer conveyance, actually a project that I've had quite a bit of involvement or been aware of over the years, and that's probably going back 20 years, is the Dawson City sewer system. They have had a historical problem with sewer sagging, and certainly they've had placement issues. And I've been part of a comprehensive sewer study completed and a 20-year capital plan developed to actually basically take the sags out. Now, what happens if you've got a sewer system that sags in an Arctic environment? That means you've got the velocities in the sewer are actually decreased significantly. If velocity decreases, any heat you have in the system, and coming out of a house, generally you'll have sewage that's probably 8 to 10 degrees C. So if it's losing heat with a loss of velocity in the pipe, that means you're going to have to deal with potential pipe freezing. And now what Dawson has to counteract that is they do what's called bleeding. So they're basically dumping fresh water into their sewer system from November through till May. And you can only imagine what the additional load on their potable water system. I think currently Dawson is probably in the range of, we'll say, 400 liters per capita per day. At one point, when they were having to put the potable water into the system for the freeze protection, their water use, I think, was up over 1,000 liters per capita per day, which is just unbelievable. As well as other project that I'm currently involved with is the Iqaluit sewer system. And they've got a historical problem again with sagging. So they have advanced design criteria and implemented those as required, but they're still looking at remedial work that is required. So this is I wanted to get into some sort of examples of the conveyance system. So the photo on the left, and you can see it's 3 pipes. This is sort of a general conveyance system. This is in Rankin Inlet. So what you have at either end of this 3-pipe system is an access vault. So these access vaults are the replacement in the Arctic conditions for manholes. Concrete manholes were taken out of service, I guess you could say now, probably 30 to 40 years ago, or they were replaced with these access vaults. So these access vaults are metal cans with an interior metal layer insulated and an outer metal layer and a metal base. These are generally worth anywhere from, I'll probably be corrected, but somewhere between $120,000 and $150,000 each. I'll repeat that: $120,000 to $150,000 each. So these are a huge expense for water and sewer systems. But what has been found are they're very robust. They can take the dynamics that are inherent in permafrost conditions. So things bounce around a bit. You know, concrete being a, what would you call it, a system that is very stiff, is that if you bounce around a bit, it'll crack and it'll leak. So the other sort of integral side in terms of Dawson is what I refer to as super pipe. So what Dawson found is that what they call normal insulated plastic pipe, and you'll see that on the upper right-hand corner, a pile of it, which is basically HDP pipe with an insulated, probably 2-inch urethane foam insulation, and then a wrap of plastic. So this was sort of the traditional product that was used in a lot of the pipe systems in the north. And just for that, you know, pipe systems in the Yukon are very common. Pipe systems in the Northwest Territories are reasonably common. In Nunavut, there's only 3 communities of the 28 or so that have pipe systems. The rest of the communities are on trucked systems. So what Dawson had implemented is that they found that the traditional piping was just not stiff enough. So they went to the super pipe. And you can see from those photos, this is the same basic pipe principle, HD pipe with a 2-inch urethane foam on the outside. And then what they did was to stiffen it up, was to put a corrugated metal pipe, as you can see around that. And anybody who's dealt with corrugated metal pipe, that's stiff, incredibly stiff. And that did, when this program was put into play, now it's probably now 30 years ago, it in fact certainly improved things. But even now, with some camera work that's been done in the last 10 years, is that this pipe is not stiff enough. So they're still getting some deflections or some in the pipe from ground activity. So the question I'm putting out there is, okay, how do you go from a super pipe to a super duper pipe? I don't know if that is even possible to make it stiffer. You could put some sort of, I suppose, some sort of beam system under the pipe. But again, you're talking about, you know, pipe that's worth upward of $3,000 a meter. Again, that's $3,000 for 1 meter. That's taking it up another notch. But just to finish off this slide, the lower right-hand corner was the type of, I guess, excavation in trying to deal with the dynamics of frozen ground with water and sewer in Dawson City. Is they put in the water and sewer, they put a sort of a drainage system and thaw stable material as they could in and around the pipe. So I've already actually explained a little bit about the access vault, and here's on the upper left-hand side, here's a herd of access vaults that have been loaded off in Iqaluit. And basically they have the same functionality as regular manholes, but I said they're a completely integral system as that center typical access vault has. They have a steel base insulated with a sump, sealed water and sewer pipes, insulated pipes going in and out, and a steel casing inside, a steel casing outside, and insulation in between. So the photo on the right-hand side is a fairly tall access vault going into a neighborhood of Iqaluit. And again, there's they accommodate both sewer and water, and the sewer systems, they are completely sealed off, but they provide access to the systems in the case of freezing. And you can see that this access vault also has a hydrant to it. And again, it's another freeze protection provision for the system of putting hydrants into access vaults as well, so that they can take advantage of the heat that comes in from the sewer line. There is no power or anything to these vaults. Any heat that comes into the system is a function of the sewer line that comes in and some radiant heat from that. But even with access vaults, as much as I've described it as being very robust, being able to take the movement, this is an access vault in Iqaluit that has taken the movement. So this is actually a critical access vault in Iqaluit that has been, you can see, is off level by a bit and sitting in a pool of water. And this is actually probably the extreme the situation, but this is what the dynamics of permafrost soils can do, is they can bump it around and there's moisture in the so-called active layer. So the remedial work on this access fault, AV305, was to remove it, bypass the water and sewer system so they can remove it and completely replace the base materials. And the idea there is to try and remove any soils that will be dynamic in terms of a freeze thaw. And generally speaking, that's a well-draining granular material that is placed and is to some depth, over excavating to some depth and replacing that. And it's a bit of a, even with the best permafrost modeling, it's a bit of a guess as to how much soil you need to remove to stabilize it, because again, it's a dynamic environment, and how the permafrost will actually reestablish itself after it's been sort of removed and replaced with stabilized material. It's a bit of a guess. But the other intervening factor in this, as you can see in that photo, is there's moisture. I don't consider permafrost ground having a sort of being a groundwater system. There is subsurface water as part of the active layer, but it's generally limited in permafrost to somewhere between 1.5 and 2 meters. So you get that seasonal thaw, but in that layer you get a lot of moisture. And as you can see with that photo of AB305, there is a lot of moisture. So this is just another sort of case study, and this is in Betchiko, Rietso in the Northwest Territories, which is south of Yellowknife. So they have a limited water and sewer system, as you can see on the drawing, and they have access faults. So this is another access fault with a hydrant, but this is sort of a camera sewer, and an example of the failing sanitary sewer is that the sewer is sagging and ponding, so that with that, and with as I've already talked about in Dawson, there's the potential of this to freeze. And a remedial work, of course, is to replace it. But in the meantime, of trying to provide some freeze protection with an introduction of additional flow. So I wanted to get into earth structures, and I think that's a very significant issue or element in terms of permafrost, because the earth, I call it earth structured for engineered water storage in permafrost, whether that be potable water or sewage. And generally speaking, the use of sort of structures such as concrete, generally not used, just because of the nature of actually producing it with the grinding materials available, or even metal tanks are not that common, although I'll present at least one example of it. But if we're talking about the types of earth structures that are generally have been used and are being used in the north, if you look at the upper left-hand side, Olokaktok, Northwest Territories, their lagoon was an original installation of an earth lagoon with a permeable berm structure. Now, again, this is old technology, and from a regulatory perspective, it's completely unacceptable, because what you've got here is a leaky lagoon, as the term goes. And from a regulatory perspective, a leaky lagoon is an uncontrolled discharge from a sewage lagoon. And the regulators very much in Canada very much insist that it has to be a controlled discharge. So this type of structure, as much as it has been applied probably in the last 40 years, has certainly not been constructed probably in the last 15 to 20 years, because it is just unacceptable. So moving from that, the next photo down was an earth lagoon with a low permeability berm structure. And again, this is material dependent on the community. And as most Arctic communities have, we'll say, limited granular or limitations on the soil available, whether it be granular material or whether it be clay, it's generally just not there. So to try and use an earth lagoon with a low permeability berm structure has limited applications. But from there, you can go to an earth lagoon, as they've done in Tuktoyaktuk, with a low permeability core. So in Tuktoyaktuk, they do have some low permeability material. And so they put that into a core and are using that as retention. But what has come into place, certainly in the last 20 years, are geosynthetics. And the upper right-hand Kogluktuk. So that lagoon was originally designed with an earth lagoon with a geomembrane in berm into the soil base. Now that design was changed before it was tendered to the structure that is generally, I guess, preferred by the regulators, which is an earth lagoon with a complete geomembrane. So that gets by having to anchor it in soil and having to anchor it, say, in permafrost, and having the potential for that anchoring system to deteriorate with time. And then the final photo is Kugaruk Nunavut. And there is more potential for this, where you use the geomembrane in the berm structure and you anchor it into the base. So you do have essentially an entire impermeable structure and then anchoring in the base. But again, you've got a point where it can deteriorate with time. So these are some shots of Gluktuk Nunavut with the lagoon system. So the big one is that the berm system has subsided on the left-hand side, 40 centimeters. The berm itself has whales, as the term is called. They've got islands of gas that have developed, well, over the last decade. And in terms of reducing the capacity they're also having a failing lagoon in several places of just slumping. And certainly permafrost has a role to play in this, but there are also other issues coming into play in terms of, again, the subsurface water that's flowing underneath the lagoon and other issues. But again, getting back to, is the problem in Kugluktuk as a result of climate change? Don't know. But in terms of it certainly is an issue, and certainly there are climate, I think, related issues with warm that are probably a challenge in trying to do remedial work, and certainly a cause of the potential cause of the system or the issues that have occurred. So this is just some more details on Kugluktuk, just to give you an idea of the issue, so that if you go around the lagoon, there is actually an original stream that goes through the site, which is actually contributing to some of the issues. The slumping on the east side of the lagoon and localized ponding. So there are a variety of issues, and it certainly is it will be a significant remedial work. And again, this is a multi-million-dollar remedial project. And the final photo is that, just looking at a cross section with the stream bed and slumping that is occurring in the subsidence. I wanted to next get into just a look at conveyance systems, and particularly the above ground system up in Inuvik. Just as a little bit of a background, Inuvik was a community, a brand new community on the in the high Arctic, near the coast. Excuse that. And the decision was made when the community was developed back in the late 50s and early 60s to go above ground. And you can see why, because permafrost engineering now 60 years ago was very much in its infancy. But there was a recognition that with the level of ice, you can see that photo on the left is an ice wedge in the ground. So with ice wedges like that, if you can imagine that thawing, is that you basically got a loss of space. That particular ice wedge could be could be 10, 20 centimeters in size. So if you do that, you're basically losing that ground. Like the ice will melt and you basically slump. And this is still evident with the system. So the original system was a wood pile above ground water and sewer system, which was also had within that wood pile, it had water, sewer, it was encased. It also had district heating, which was taken out of service. So the replacement for that, which was put into play probably 30 years ago, is what you see on the right. So that is a dual system, water and sewer, in again, insulated pipe, but it's got a metal jacket, and it is suspended on brackets and rollers and go around the system. So this is, I would call it the centipede system in Inuvik. And this was in response to replacing the above ground system. And this system in Inuvik generally is $8,000 to $10,000 per meter. I'll repeat that, $8,000 to $10,000 per meter. Hugely expensive. But you can see in terms of the modern degradation of the permafrost with that photo in the center. There's two red lines. So the piles were the piles were painted black in the original installation, and then of course just rust protected below that. So you can see that's probably anywhere from half to 3/4 of a meter that they've had subsidence in the Inuvik pile system, just with the deterioration. And these piles, I think these ones are probably going down about 6 to 8 meters. So they're grounded in permafrost and stable, but the ground around them, of course, can subside. But this is now where Inuvik is going with the next generation of the pipe system. So there has been a new outfall sewer that has been constructed in the last 5 years. And one section of the sewer actually goes through an area that has an estimated very significant potential for sewer subsidence. So what you can see in this one is thermal siphons. So those are the pieces of pipe that are coming out with an angle then going up to a flare. So these are actually a geothermal means of maintaining the permafrost at depth. So those are along the sections to try and maintain that permafrost. But what is really interesting is that the actual pipe support system has changed. So the one on the upper right-hand system is what has been used now for the last 30 years. So it's got support in the X and Y. So in the vertical position, it's got screws that you can change the height, adjust the height if there happens to be any movement in the pile, and then it's on a roller system. So you actually get an X and Y adjustability. Now with this new sewer system, they've gone X, Y, and Z. So the X and Y is still the same as in the previous system, but now they've got that long rod going across the pipe supports. That's the Z, and it's mounted on a screw system. So if that pile actually shifts in one direction, they've got full adjustability. And the other, this is getting to another, what I call it what is happening now in Inuvik, what has always been there is adaptive conveyance system, but they've taken the adaptive system and now gone to sort of from 2 dimensions to 3 dimensions. This is the water storage tank recently in Inuvik, and it is now, it was constructed on actually using some more traditional insulation. So the native soils between that are actually on permafrost ground, so they're subject to changing and shifting around. So that's not good for any large water storage tank. But you can see the pipe, the holes, or the covered holes along the bottom of the tank, and those are actually culverts that are uncovered in the wintertime. So you're getting a flow of cold air through the tank, or the foundation of the tank in the wintertime, and then in the summertime they're sealed off. So in the profile, you can see that this passive cooling system of a 450 millimeter CM corrugated metal pipe, it goes through the base of the tank, and it's 2 meters thick, just to add an insulation to the ground. But what in terms of an adaptive storage foundation is that there has been a conduit for a future consideration of a thermal siphon installation. So basically the pipe is there to allow a thermal siphon, as we saw in that other system, be installed in the future. And I know I'm at the 30-minute mark, and I could keep, I just wanted to maybe speed it up a little bit. So another, in terms of example of water supply, and this has been an issue in Iqaluit for probably a decade, is that the original water supply reservoir, referred to as Lake Geraldine, no longer has capacity for the community. And certainly it can be generally presented that the general capacity is because of the growth of the community. And Iqaluit has certainly grown leaps and bounds over the last 40 years. So in providing some supplementary water to that, they've had to go into locations away from the community. And in this case, there's a river called an Apex River, which is to the top of that photo in the middle. And now they're refilling the reservoir on a regular basis, well, probably seasonally, from that river, but that river has a low flow. So now they're looking at an unnamed lake as the supplementary water supply for Lake Geraldine. But again, on this one, Apex Lake or Nuniakukuk, I can't pronounce it too well, is has a low flow and probably may have a lower flow because of climate change. But having to have this supplementary water supply, and ultimately they'll be constructing a new raw water reservoir adjacent to the community. This whole, and it's not a remedial, this whole increase in the supply and capacity is probably worth somewhere between 60 and 80 million dollars. And it's a project that is needed as soon as possible and probably be completed over the next 5 years. So this is part of a funding that has been provided by the government of Canada. Back on April 1st, Monsieur Trudeau was on the addressing council on April Fools, believe it or not, and he said we have $200 million available for the community over the next 5 years. I was figuring that Trudeau would have called back a week later, and again, being facetious on this thing, saying April Fools, but he didn't. So they've got a large project to complete in terms of their addressing what, which is a water supply issue that probably has elements of climate change. In dealing with the potential impacts of climate in Iqaluit, and their system is completely buried as opposed to Inuvik, and Iqaluit does not have the considerable ice contact that Inuvik does. But over the last year, Iqaluit had an investigation completed saying, okay, what about above ground versus below ground servicing, in terms of retrofitting the community or doing it new? And I was part of the study that just looked at, again, from a feasibility study of going above ground versus below ground. And this particular new subdivision area, that the above ground budget came out at about $60 million total, which is about a cost per square meter of development of about $600. And below ground, it was about 40 million, which is about $300 per square meter. So just on this overview, that below ground systems are still considerably less expensive to install. So as part of this investigation or consideration of some of the ground movements that are going on in Iqaluit, the National Research Council has an instrumentation program going on with any new pipe that's in place. And the photo on the right-hand side is actually a new piece of sewer that's going into Iqaluit that went into Iqaluit last summer. So you can see that, and we've already talked about, it's an insulated HDP pipe. You can see the permafrost boundaries. You go down the cross section where you get that dramatic change in materials. This material is the materials are joined with electrofusion couplings. So these are basically couplings that are put between the joints, and then power or current is passed through them, and it joins the pipe. And the other alternative is butt fusion, where you heat both ends and join them together. But these photos look at the instrumentation that is being installed by the National Research Council on their program, and basically the means to measure movement and record it. And just in the way of getting data, and I think that's something that most Arctic practitioners know about, is that there is a considerable absence of data in the Arctic. And if you don't have data, you really don't have the ability to, apply science and engineering to problem solving. You were saying, okay, we may be trying this solution. Certainly something that's being implemented in Iqaluit is collared systems coming out of the pipes that allow for movement. The term doesn't come to mind in terms of immediately, but basically, a number of joints coming out of the pipe. So there is a dynamic that can be used for observing any movement. This is just another example that I talked about a little bit already, was the water supply in and around Yellowknife. So Yellowknife, the photo on the right-hand side, they take their water 8 kilometers from the community. because there's a legacy issue from the giant mine in terms of a sediment that is highly arsenic contaminated. And this is sort of another big, well, potential issue in terms of that water supply and the contamination, the arsenic contamination. But again, where they're providing it now, they're well above where the contamination is. But, is there some issue that could arise in the future? Going well up the geographies, it's up to Grise Fjord. So Grise Fjord, and this was a problem that came in back in 2008, is that they were not allowed to, or say they didn't have additional water available to refill their 2 tanks that you can see in the upper photo on the photo on the left. They did not have to enough capacity to refill from the local stream, so they were harvesting water. And you can see the forklift out on the ice, harvesting an iceberg and putting it into the tank. This is a reoccurring problem, and they've got an issue with their water supply and looking at switching their water supply with a seasonal refill, find something that has a larger supply. And in the final geography, going up to Longbarden-Svolvær, Norway, water supply. So they're looking at alternate water supplies there, and just more of an information that this is not a Canadian Arctic problem. There's issues in Alaska, and there's also issues in Greenland, and issues in northern Norway on the island. This is just some photos there. So I wanted to, in terms of, I guess, winding this down, in terms of a compilation of components, impacts, and responses, and just go through. And again, this information is all available in the presentation, and of course the report that I did for NRC. So in terms of the source, you've got elements of the river, lake, and ground, and of course in the ground in the Arctic context, there is no, in Nunavut with permafrost, there is no groundwater generally available. So within that, you've got water quality, water quantity, and in terms of responses, trying to develop a resilient water treatment systems for changes, resilient water supply systems for potential reductions. So this table goes down and looks at the various components and those elements. For wastewater infrastructure, a similar collection. You've got trucked, piped, bagged, and you've got road access, ground with buried systems, ground with above ground systems. So similar elements, adequate drainage systems for roadways, resilient pipe systems for buried and above ground. And again, I won't go through the remainder of the systems, but generally similar look and compilations for components, impacts, and responses. And the final one in terms of water infrastructure and issues and gaps. So the source, river and lake, alternate water supplies for communities. This has been investigated and is certainly ongoing in terms of, are there contingency water supplies? And there are knowledge gaps of alternative water systems. Raw water intakes, systems damaged by ice-related factors, alternative intake systems, and then water storage, whether it be earth, rock, or steel. That raw water systems that have evolved over the past 30 years on a case-by-case basis. Earth systems are most commonly used, but again, alternate configuration of materials. And the photos on the bottom, which I think are always more indicative, is this photo of the failing lagoon system in Kugruktuk, which ultimately had to be relined, and this was the seepage that was occurring. Issues and knowledge gaps. So I'm now at 42 minutes past the hour, and getting into time. I think our sponsors would like to have that period for at least some questions and comments. So I'll try and wind it down a little bit quickly, but mainly the same things for water infrastructures, issues and gaps for collection, preliminary treatment, primary treatment, issues and knowledge gaps. So as a sort of a final closing, it is anticipating that Arctic climate will influence the quality and quantity of Arctic community water. A significant number of communities, as already pointing out, have experienced water issues that may be related to climate changes. The most recent climate change report states that the entire Arctic Ocean will be relatively ice-free by 2030. And the number I hear that in 2016, the temperatures in the, in fact, 6 degrees higher than average. So I always thought it was 4, but this is a little bit better. So in terms of this presentation, in terms of its hard copy that anybody can get from me, and those 2 emails, or they can request a copy of the NRC report and those 2 emails. But this image shows a color-coded map depicting climate change modeling over the last probably 60 years, and certainly focusing on some very, very dark related areas, particularly, I guess you can say, in the sort of the end of Northwest Territories and the Arctic coast areas where my original photos were taken. And that is the end of my presentation. Thank you very much for your patience. For additional cold regions information, you can go to issue.com, CryoFront, and we'll say there's a wealth of information on that website. I'll turn it back to the moderators as my voice begins to fade.